Can I ask everyone who is interested to be seated? Thank you very much. All right. Sorry to get between you and your food, but we're running a little bit behind, so we have to compact things together. So my name is Misha Sitrakian. I'm one of the founders of GridGain Systems. I also run engineering at GridGain. I'm also chair of project management committee at Apache Ignite project. So today we will be talking about in-memory data fabric. Nikita mentioned some advantages of in-memory computing. I will be talking about in-memory data fabric in the context of an actual product, Apache Ignite. I'll be covering various components within Apache Ignite. I'll talk about data grid, compute grid, service grid, streaming, and we'll also talk about some of the pretty cool Hadoop and Spark integration we have in Apache Ignite. And at the end, I'll show a quick demo comparing Apache Ignite SQL to Spark SQL, and we can discuss the differences and some of the results towards the end. So if you have any questions, please raise your hand. I'll do my best to answer it as we go. So let's get started by defining what data fabric is. So essentially, I'm going to be repeating some of the stuff that Nikita said, but essentially, the only reason you would use a data fabric like an in-memory data fabric is to get performance and scalability. So we make things faster by executing them in memory, and we scale them out horizontally, virtually without any limit. And we do it by providing a collection of in-memory components. All these components are independent of each other, and it can be used separately, but all of them work very well with each other and very well integrated with each other. For example, if you take one of our most used components like data grid and compute grid, if you need to send a computation within your cluster and that computation needs to work on some data, you want to make sure this computation arrives exactly to the node where the data resides, exactly to the node where the data is cached. And that's exactly the type of integration that we provide within Apache Ignite. We collocate your compute with data, we collocate your streaming with data, your services with data, et cetera, et cetera. So we're all about collocation, we're all about minimizing traffic. In the absence of this integration, you may arrive to the wrong node, you may start carrying data around between nodes. That actually may hurt the productivity, may hurt the performance, instead of improving the performance. So the integration between all the memory components does matter. Besides all these components, all this rich feature set, the project actually is very easy to install. It comes as one zip file. You just download it, unzip it, and you're ready to go. We try to implement all the standard APIs, like sets, maps, queues, all of them in distributed fashion. We'll also implement GSR 107, which is a JCP standard for local caching in Java. And we'll also add distribution capabilities to it. The project is fully Mavenized. It only brings one mandatory dependency into your application, the mainly Ignite core.jar. And then other dependencies you bring on an a la carte basis. Let's say you need Spring configuration. You need to configure Ignite using Spring XML files. Then you drag in, you'll bring the Spring dependency. You need to use Hibernate for persistence. You would bring in the Hibernate dependency. But by default, Ignite does not require this component. It runs on its own. And lastly, I want to mention that there are no hardware requirements to Apache Ignite clusters. You can deploy an Ignite cluster on a heavy loaded server, let's say 500 gigabyte, 64 cores, and we'll take the resources you make available to Apache Ignite and make the best use of them. And or you can run a cluster of 10 gig servers, maybe with 4 cores. And again, you can actually, ironically, can cache as much data on that low-end cluster if you actually add those servers together. So we will take and utilize the resources you make available to us. Always say the more data you cache, the better the performance gets. But generally speaking, we will utilize the memory you provided. If you look at this jigsaw puzzle, these are the in-memory components Apache Ignite provides, DataGrid being one of our main components. Essentially, it's a distributed key value store, distributed cache. Let me ask you a question. How many of you actually heard the term DataGrid before? All right, good. In-memory caching? Okay. All right. So about the same thing, DataGrid adds extra features to the cache, like extra distribution, transactional features, querying capabilities, etc. And we'll talk in some detail about DataGrid, being that it's all about data distribution, and you rarely have a project without having to process or to work with some data. There's also Compute Grid, which actually computes on the data. It provides for-join and MapReduce type APIs for computation. There's Service Grid, mainly for deploying singletons on the cluster. There's Streaming component for ingesting data into Ignite cluster in high volumes. There's the memory file system. There's Spark ICTs. There's Hadoop acceleration. So all of those components are available within Ignite. We'll talk about some of them, and I'll start with DataGrid and some other data fabric components, and then I'll move to Gridpool, Spark, and Hadoop integrations, and then to demo. So let's talk about the DataGrid. Essentially, as I mentioned, we implement JSR 107. What does it mean? So JSR 107 is a Java standard for local caching. It provides concurrent map APIs. The APIs are very similar to Java util concurrent map. And so you would get methods like putFabs and replace, remove. All of those APIs are there. It also provides some event notifications, some mechanisms for collocated processing, but essentially it's just an API for local caching. It doesn't have any distribution semantics or transactional semantics or querying semantics for that matter. And that's exactly what Ignite DataGrid adds. It is, so if you think about Ignite DataGrid, it's a distributed key value store. It adds, on top of basic caching operations, it adds asset compliant transactions. There is, at no point in Ignite you will have an inconsistent read or inconsistent write. The data is always consistent, regardless of where the crash happens, whether it happened on the client side, whether it happens on the primary server or on the backup server, or anywhere in between, or on all of them. The transaction will either commit as one unit, the whole transaction, and it will fail as one unit. The whole transaction will commit or fail as one unit. Moreover, if you have a database underneath, a lot of users use Ignite on top of an existing database, like maybe Oracle database or MySQL or MySQL. Using database underneath Ignite, database joins the same transaction. So you update memory and database together as part of one transaction. And by the way, memory is distributed. And if anything at any point fails, then the whole transaction will roll back. Yes?
So, quick question. I see a point there saying SQL queries, ANSI 99. Does Ignite actually do SQL query processing on its own, or it just pushes this down into other?
So the question is whether Ignite has an internal SQL processing, or does it push it down to another storage? So for all intents and purposes, I will say that the SQL processing happens inside of Ignite. We have our execution plan, we have SQL parsing, and we have indexing. We distribute the SQL queries.
So do you have a query optimizer?
Yes.
Okay.
We have an execution planner, and which will pick the best indexes, whose job is to optimize queries.
Okay.
All right. So now, given that we move to SQL, so Ignite is ANSI 99 SQL compliant, and I will be showing some of the SQL examples for the of the queries supported on top of Apache. And also with Ignite comes automatic RTBMS integration. So it integrates with underlying databases, RTBMS systems automatically out of the box. You don't need to write extra code. However, if you have other data storages, maybe Cassandra, maybe Mongo, maybe just file system, database, the persistent layer is a pluggable component within Ignite. So you can always take the interface, it's called cache store. And by the way, it's part of JCache standard. So You can take cache store and plug in your own implementation. Question?
Yeah, this might not be the appropriate time to ask, but some questions about like the write behind and write through capabilities.
Yes, that's actually a good time to ask a question. So the question was, how does Ignite integrate with database, in what fashion? So whenever an update happens in memory, it gets automatically propagated to disk, to database. That feature is called write through. Whenever a read happens in cache, and it's not in memory, it will get automatically loaded from database and then stored in cache and returned to user. That feature is called read through. There's also a write behind kind of functionality where you do an update, but instead of going to the database right away, you cache these updates in memory, you accumulate them, create a batch, and then flush it out to database as one. Obviously to reduce the load on the database and to improve performance. So read through, and write behind are the three ways you would interact with database. Question?
So when you run a query that might have to fetch data from different databases, do you actually do data blending in Ignite against multiple data sources?
I'll actually talk about SQL a couple of slides down, so we'll get a chance to all discuss all that.
Right.
I want to just answer the questions relevant to this slide, and we'll move to SQL, I promise. Did you have a question?
Yeah, again, maybe it's something I can ask, but specifically with the write behind implementation, does that consolidate, like say I have, that's configurable, right? Like say I want to do a write behind every 5 seconds or something like that?
Yes.
So does it basically compact all of those write down to only the most recent update, or is that configurable to like all of these writes that I take, can I persist all of those effectively those events to my data store?
You know what? I wouldn't. So the question is, when we do write behind, if you have multiple keys in a batch, does it consolidate them in one operation or multiple operations, multiple updates? And actually,
sorry, sir. Specifically one key. So say I have one key and I have multiple operations that happen on that one key. Let's say I have like one key and it's X, and I set it to 1, then I set it to 5, then I set it to 4, then I set it to 10. And the last one that I did was write. Does it only write the 10, or do I have the capability to write all of those events as well?
you know what? I do not know.
Okay.
So the question is whether, if you have 4 updates of the same key, whether we do 1 operation to database or 10. And I'm going to actually ask one of engineers, do you know the answer to this?
I think the answer is no. Like, I'm 99% sure.
It compacts down to only the most recent write, for example?
No, they will go just, as you update the cache, so if you have several updates for the same key, they will go the same. You will have several updates.
You don't have a
For the
choice.
database?
All right.
Oh, that's
So the answer is, I'll summarize. The answer is, we do not consolidate them into one update, we make them separate.
There is no choice here. If you batch together updates on multiple updates on the same key, you might break transactional integrity. That's completely out of question if you want to maintain transactional integrity.
There's no transactional integrity with the write behind, right? Because ultimately what you're saying is I'm going to accept an asynchronous update to my data store.
That's not true.
That is actually true. When you do a write behind update, when you update memory and then asynchronously later on update database, you cannot have, so the memory transaction commit and then database updates at some point later. That's the write behind functionality. If you do write through, then that would not be true.
I'm sorry, I disagree.
So let's actually move on. I think we give this one to them. Let's take a look at how data is distributed within Apache Ignite. So we have an example here where we have 4 servers. We have 4 keys, A, B, C, and D. And Ignite will automatically distribute evenly those keys across multiple servers that you have deployed in your cluster. And note that we also evenly distribute backups, but we do not have a notion of backup server. For us, we back up at a key level, not at the server level. So for example, if node 1 had 10 keys, then 3 of them could be backed up on node 2, 3 of them could be backed up, the other 3 could be backed up on node 3, and etc. So the backups are distributed. At a key level and not at the server level. Why we do it? So in case of a crash, in case of one node leaves, the load for the data remains to be evenly distributed within the cluster. Did you have a question?
Yeah. Do you handle asymmetrically sized servers, or do you require all of them to be identical?
No, so the question is, do all the servers have to be identical within the cluster? The answer is no. You can actually configure some servers to hold more data, some servers to have less data. If you do not want to tinker with configuration, then by default they work with all. Ignite will assume that all the servers are evaluable. All right, so let's just take a brief look at how a client would access data. Let's say client wants to get a key A. He checks the near cache. We have a notion of, so the server side is caching all the data in memory, but we'll also have a notion of a near, smaller local cache on the client side. So if a key A gets accessed, we check the near cache first. If data is not in near cache, then we go and fetch it from one of the servers. In this case, for key A, we'll go to JVM1, because JVM1 is the primary owner for key A. We bring it back, cache it, and return it to user. For key B, for example, it's already present in near cache, so we don't have to go to the server. We fetch it directly from client-side memory and return it. The near cache is also transactional, maintains all the transactional semantic of Apache Ignite. You do not need to use any additional APIs. So the way you just configure near cache to be there, and all the APIs, all the usage remains the same. Question?
Yeah. How often and when do I see updates to this key B if I have it in my near cache?
How often? Are you asking how often?
Do I see each and every change on the remote key B, or do I only get point-in-time snapshots, or is it invalidated?
So the question: how often does near cache key gets updated? Key value pair gets updated every time the corresponding key value pair gets updated on the
So
server.
the server is aware of all the near caches.
Yes, the server is aware of all the near caches.
So when you say near cache, is that when you configure that you want to allow near cache reads or read, like, is that like read from backup, or is that specifically when the local client makes a call to the specific owner of that key or that partition, right?
So the question is, how does near cache essentially work? So on a client, so the caching, imagine a data farm, right, where you have heavy-end servers all caching a portion of the data, like here. And then you have thinner clients, like a smaller client, connecting to that data farm and accessing for data, processing data, querying data. And on the client side, we will also allow you to have a smaller cache. That's a smaller LRU cache local to that client. So it has nothing to do with the server-side cache. So whenever data is absent in a client cache, the client is intelligent enough to go to the primary owner for the key, fetch it from a server, and then cache it on the client.
So, but don't you run into a split train problem then? If you have
Sorry?
So don't you run into the split train problem then if you have transactional data that's sitting on?
We actually, so the question is about split brain network segmentation problem. We actually have a good solution for network segmentation problem. I can talk about it, but let's push it out towards the end because it's going to take a little bit of time. Question?
So if a node crashes, do you re-replicate the data that was in this node? And in this case, who maintains what was in this node? Like, for example, node, you had a replication factor of 2. One node goes down, and then do you re-replicate the same keys that was there to another node?
So the question is what happens in case of a crash. If a backup crashed, what happens? So in case of a, did I understand the question correctly?
Yeah, so what, for example, this node crashed, and then you already know that A, B, and C was another 3 nodes. Do you re-replicate those again into another node?
So when you say this node, do you mean client JVM or server?
Another node. So for example, every key had a main value and a backup.
Primary cut and backup cut.
Primary and, yeah, exactly, and secondary. So the primary went down. So it's a secondary now is the primary.
Then
you need another secondary?
Then, yeah, so let's say you have a primary and 2 backup copies, and primary crashed. The first backup will become primary, the second backup will become first backup, and a new backup will be assigned, and the data will be transparently in the background migrated to the newly assigned backup as well. Cluster remains operational. As long as you have at least one copy, cluster remains operational, there's no data loss.
So how do you map keys to
nodes?
To nodes.
So the way, so the question is how the keys get mapped. Initially, when we started out, we used consistent hash. How many of you have heard about consistent hash? All right, some hands. Essentially, what consistent hash allows you to do is it allows you to about evenly distribute the keys across the cluster. And the main point is when topology changes, the data movement between nodes is minimal in case of a consistent hash. However, it turns out that consistent hash is not all that even. and they're better algorithms. We recently, about a year ago, switched from consistent hash to rendezvous hash. Exactly the same feature, exactly the same end result, but rendezvous hash provides better data distribution, so we use rendezvous hash now by default. So the data, so we do not keep key to value mappings. We do not have a notion of main node like Hadoop does. For us to determine which node the key belongs to, we take a key object, get it hash code, plug it into our rendezvous hash function, get a node back. That's the node for that key, we go to that node. So it's a stateless function. It does not grow if the data grows. You can cache terabyte of data or 10 terabytes of data, and the function will still work the same. More questions? All right, let's move on. Replicated cache, yet another way to distribute data in memory. So in the first example, with partition cache, we actually took the whole data set, split it into multiple pieces, and assigned each piece to individual node. So this way, the more nodes you have, the more data you can cache, and every node owns its own piece of data. In a replicated cache, however, we simply take the whole data set and cache it on every node. We copy the whole data set to every node. Of course, the advantage of this approach is that the data is available on every node, so wherever you go, you can do the read. The disadvantage of this approach is that writes become very expensive. In partition cache, whenever you do an update, like in this example, whenever you do an update, all you need to update is a primary copy and a backup copy. You have 10 nodes in the cluster, you do 2 updates. You have 1,000 nodes in the cluster, you still do only 2 updates to update the key. In a replicated scenario, you have 10 nodes in the cluster, you do 10 updates for a single key. You have 1,000 nodes in the cluster, you do 1,000 network trips to do updates, because every node holds the same copy of the data. So all the nodes have to be updated. So replicated cache should not be used in scenarios when writes are frequent. You should use replicated caches when your use cases read mostly, and the data set is relatively small and can fit in the memory of one node. So lookup data, reference data are good candidates for configuration data, good candidates for replicated cache. And generally, in a typical deployment, you will end up with some combination of the two. You may have maybe 10, 15, 20 partition caches, maybe 5, 10 replicated caches, and they can coexist together very well. You can transact across multiple caches. You can have a transaction that spans multiple caches. You can query across multiple caches. You can do distributed SQL joins across multiple caches, aggregations, group bys, having clauses, etc., etc. So multiple caches. So cache is just a bucket where the data is stored. You do not lose any functionality by splitting your data into multiple caches.
We don't support transactions across a replicated cache, though, right?
The question is whether transaction across replicated cache is supported. The answer is yes. In Ignite is supported. In Hazelcast it is not supported. So I'm assuming you're coming from that background.
Yep.
Okay. Just a guess. All right. Did you have a question?
Yeah. Do you support like broadcast HTTP for updates in this scenario?
In a replicated scenario? No, not. We use TCP/IP mainly for communication. There's no real benefit to use anything other than TCP/IP. Any more questions?
So there seems to be a fair amount of overlap between what you're describing Ignite to be and Spark. Can you address
We'll
that?
talk about Ignite and Spark. There's actually, in this scenario, there's very little overlap because
I understand.
Spark doesn't do transactions at all,
Right.
But there are some similarities, and I'll cover them, and I'll actually describe how Ignite, a cool way Ignite can work with Spark. We actually provide very cool integration. All right, let's move forward. Off-heap memory. If I'm sensing there are quite a few Java developers here, so you guys know what garbage collection is. And you know that if you allocate more than 16, 20 gig of RAM to a JVM, you have to meticulously tune garbage collector, and all you're doing is simply postponing the inevitable. At some point, the log the world GC pause will hit, and your cluster will freeze. In our test, if you deploy 10 nodes, each node has 50 gig of RAM. On that type of cluster, 50 gig, 10 nodes, you can get a garbage collection pause of about 5 minutes. obviously very bad for SLAs, unacceptable for any type of production scenario. So to fix that, to avoid the garbage collection process, we store data off heap. We still in memory. It's still one pointer reference away. It's very fast to access that data. The format we store is the same as we do on heap, except now JVM doesn't know about it. And obviously then, since JVM doesn't know about it, we cannot have any effect on garbage collection. So the way you work with off heap, you would allocate as much memory as you would if Ignite wasn't even there. And then you tell Ignite how much memory you want to use off heap. 2 GB, 1 2 GB on heap, 200, 300 GB off heap is a perfectly good configuration for this type of scenario. And this is part of open source, unlike some other competitor projects have a part of enterprise edition. This is part of our open source edition, so do check it out. One of the cool features that we have recently released, I want to mention, just give this feature a plug because I believe it's a very useful feature, is a deadlock-free transaction. If you're using transaction, if you're doing any type of distributed locking, then you're aware that if you acquire locks, or non-distributed lock can also fall into this category, but if you acquire locks in the wrong order, you will end up in a deadlock scenario. If you're doing a transaction, and if one transaction updates key 1 before key 2, and the other transaction updates key 2 before key 1, will lead to a deadlock. At some point the cluster will freeze. So you constantly have to worry about the order of updates within a transaction, or the order of locks that you're acquiring from your application. With deadlock-free transaction, we actually solve that problem. We introduce a fail-fast mode that never acquires a single lock. Essentially, we optimistically allow most of the transactions to complete. In our experience, we've been deployed in many environments, in many large banks, small banks, various other systems, and most of the systems have very little contention. So most of the transactions will go through with zero contention, and very rarely you will get a case when some keys will be, the same key will be updated in multiple from multiple transactions at the same time. And in that case, with deadlock-free mode, most likely we'll still figure out a way to order them up and actually proceed one before the other, process one before the other. In case if we cannot make a decision, deterministic decision, which one goes first, in that case we'll simply fail the transaction, you'll get an exception, transaction will be rolled back and you can retry. So this is like type of optimistic failure that allows you to work update your data without without worrying about locking, order of locks. Very good for large projects. In my experience on large projects, you have multiple components, all accessing cache in whatever order they like. They have very vast API. API mostly is business API, not even data access API. It's mostly like a business logic API. And then this business logic, the various components perform this business logic in whichever form, in whichever order. Worrying about log order or transactional update order in those cases is almost impossible, especially on large data sets. So on large projects, so this actually solves it. Another cool feature, we added a binary protocol for a very compact protocol for storing data in memory, and it's cross-platform. So you can do .NET, you can store data in .NET, you can store data in C++, or you can actually update data from C++ and read it from .NET and Java. And one of the differentiating features here is that we do not treat .NET or C++ as clients. For us, it's a full-blown data grid. You can do transactions from .NET. You can do, you can even execute .NET closures on your server farm. And we'll show the closure, and we'll execute your .NET closure on top of a data grid. You can do persistence with .NET. So the goal here is if you're doing .NET or C++, you do not have to write a single line of Java. We're not quite there yet, but we're almost there. So SQL, as I promised, very hot subject. So as I mentioned, Ignite is ANSI 99 compliant. There's virtually no limit of type of SQL you can run on top of Apache Ignite. You can do distributed joins, you can do group bys, handling clauses, you can do all sorts of aggregate functions. All of that is supported within Ignite. we index data in memory. So essentially when you put data in cache, your class becomes a table, and the fields become columns. You tell us which columns you want to index, and that's where you get the performance. If data is indexed, the queries will work very fast because indexes are also in memory. The data in memory, the access is very instantaneous. We can process thousands, tens of thousands of queries per second on top of Apache.
And so, what is the meaning of ad hoc?
You do not have to predefine your SQL queries at startup. You can actually come up with them as you go. So that you can essentially start up with that cluster, populate data, and then run ad hoc queries, like at-will queries on top of Ignite cluster. We also provide JDBC and ODBC APIs. We support Ignite comes with JDBC driver and ODBC driver. So tools like Tableau can integrate with Ignite using ODBC driver. And various JDBC clients, whichever standard SQL client supports JDBC or ODBC, it can connect to Ignite cluster and can start doing queries of the data that is in memory. Some of the examples of SQL. For example, here we're doing showing off that we can do any type of SQL function. Like here we're doing concat, concatenate first name and last name. We're doing a distributed join between person and organization. This is just probably one of the smallest SQL queries you will run on top of Apache Ignite. You get a cursor back, and then you can iterate through cursor in a paginated form or get the whole data back. Another example of SQL, you can, here we're doing a join, we're doing group by, we're doing order by, and we're doing some averages or mean, man, and average of salaries within one organization. Again, you get a cursor back and you iterate.
Can you show the C++ syntax for this? Because this is Java syntax, right?
So it's not a Java syntax. The SQL is SQL. I'm just putting it in a Java string. But,
well, I understand, but the wrapper is in Java syntax, right?
No. C++ API would be identical. You would just put a string, provide a string of SQL to C++ API and pass it in.
The query cursor you're defining there, that's Java syntax. You can't put a question mark.
As I mentioned, the APIs, but we try to actually have parity in API between .NET, C++, and Java. So most of the APIs will be identical when you switch between platforms.
Okay.
Yes?
Is it only equi-joins, or you can generally theta joins are also supported?
You can do inner join, outer join, joins based on equality.
Like bigger than something, something bigger than something?
Well, you know what, I guess, can you do a join where one key is bigger than another key?
Yeah.
I do not know, actually, the answer to that question. So I'll have to look that up. Maybe after the presentation, you can ask Valentin, one of our engineers.
Can you do partition joins?
So you can do cross-cache joins. Cross-partition. Cache has multiple partitions, so the answer, I think, would be yes. So you can do joins that on collocated keys. And are you asking about joins across non-collocated
One
keys?
thing related to this, I think if you can join, say, one table and another based through the cross product, if the answer is the yes,
Yeah.
the answer to that would be yes.
So
The
yeah,
problem
you can
with
do that.
the problem with non-equi-joins that you cannot partition. Like with equi-joins, you can partition based on what are your.
Yeah, so I do not know the answer to your question, to be honest. So you can do joins across the cluster, across the partition. Mostly I've seen equal joins. Most questions come about that, and most users use them, so not sure what the answer to your question is.
Well, however,
maybe no.
However, if you can't do non-equi joins, then you're not SQL 99 compliant.
All right.
So,
And you are.
well, you made a claim that you are
Then
SQL
we, I guess,
99 compliant, right?
if we can do them. I do not know if we can or cannot. So let's postpone that discussion. Let's postpone that technical disqualification of SQL 99 compliance today. But syntactically, it's SQL 99 compliant for sure. All right, so let's switch to Compute Grid. I'll go very fast now because we're running out of time. Essentially, we covered Data Grid in quite some detail. A Compute Grid allows you to do computations on the cluster. You can actually execute jobs and closures, runables, callables on the cluster under load, thousands of computations per second, tens of thousands of computations per second actually. So it supports anything from just a simple closure, you can execute on a Java 8 lambda across the cluster, to a fork join or map reduce task. This diagram actually shows a fork join task. You take a task, split it into multiple jobs, run it in parallel on multiple nodes, get the results back, and return them back to user. This kind of approach calls for fork join. And what it is, it's actually a special case of a MapReduce API, of MapReduce paradigm, where both mapping and reduction happen on the same side. Most of the time, we're noticing that this approach works a lot faster than MapReduce, simply because MapReduce was never even built for performance to begin with. So that's from an API standpoint. Underneath, there's a lot of complexity that happens. First, I should mention that we have a guarantee that as long as you have at least one node standing, no job will ever be lost. So there's a strong fault tolerance capabilities there. There are load balancing capabilities, checkpointing for long-running jobs, etc. So very powerful API. And on top of that, if you're accessing data, then we automatically collocate your computations with the nodes that are responsible for caching the data. So there's no data noise that gets created when integrating compute and data grid. So let's move forward. Streaming and CEP. So essentially the main use case for streaming is ability to ingest large amounts of data into your cluster. Right? The data is continuous, the data never ends, so you rarely can feed all the data in the memory, and so you have to make sure that the data can pass through the memory. And that's where the concept of sliding windows comes in. And we implement sliding windows on top of data grid. We actually implement a lot of features on top of data grid. Sliding windows is just one of them. And given that sliding window is implemented on top of data grid, all the features available on data grid are available here as well. You can do SQL queries between sliding windows. You can do transactions on sliding windows. So essentially, as data passes through the sliding window, you can query it, you can transact on it, you can maintain all sorts of atomic aggregates that are typical for streaming use case. So all that functionality is available here. And we also integrate with many data sources. Camel, MQTT, we integrate with Flume, we integrate with TwitterStream, with Apache Kafka. So all those data sources are integrated with the streaming. Even if you don't have a continuous use case where data continuously comes in, and you just have to load a large data set in memory, you would still use Ignite Data Streamer API because it's the best way to load large amounts of data in memory.
Can you provide, do you provide streaming rate guarantees, such as I want to be able to process 1 gigabyte per second. I know that my data source is going to deliver 1 gigabyte per second. Can you?
You can tune the system. I mean, it's
no. Well, tuning is not the same as doing this declaratively.
The way that the guarantee we provide is that we provide at least once processing guarantee, and if you use sliding windows on top of transactional cache, then you can get to at most once transactional guarantee as well.
Can I get exactly once? Exactly once.
In a transactional use case, yes. In a transactional use case, you will be able to get exactly once, and at most once, and at least once, because everything happens transactionally. So let's move forward. Let's switch to service grid. Essentially, the main feature here is singletons within the cluster, so you can deploy services that are highly available within the cluster. In case of a node crash, the service will automatically pop up on another cluster node. So I'm going to move very fast. Slide about benchmarks. Just want you to know that we constantly benchmark, and Ignite is overall very fast. Because how do we know it? Because we check it ourselves. Do check out our benchmarks on Yardstick framework on GitHub, or you can also visit the Apache Ignite website. All the benchmarks are published. And now I want to talk about Spark integration. I have a couple of slides. Mainly, I'll start from the fact that Ignite integrates with Yarn and Mesos. So if you use Spark and Hadoop environments with Yarn and Mesos, Ignite will automatically plug into those environments. And now let's talk about a pretty cool feature called shared RTD within Spark environments. So essentially Spark is very good about doing computations in parallel. What Spark is not good at is sharing state across multiple jobs and tasks or applications that are running across multiple Spark nodes. And Ignite is actually, on the other hand, is very good about sharing state. So what we thought we should do is provide an RDD API or on top of Ignite cache, and so you could natively use it inside of Spark in your Spark environment. So you can actually instantiate Ignite RDD in your Spark environment, load it, update it, and whenever you update it on this server, the other server will see the update. And moreover, just as a side effect of this feature, because Ignite supports in-memory indexes and Spark doesn't, the SQL for Ignite that you can run on top of our RDDs is a lot faster than you would get on top of Spark RDDs or data frames. And I'll actually demonstrate the example. Any questions on this? Moving on. In-memory file system, if you guys are familiar, how many of you have heard about Tachyon? All right, so Tachyon provides an in-memory file system. We also provide an in-memory file system. Our file system is based on top of a data grid, same type of partitioning. And it's the same kind of approach. You can see, you can use it standalone. It plugs in into your Hadoop installations. It implements HDFS APIs for file system, for using file system in Hadoop. And it actually can automatically persist to HDFS if you need it. When to use which, when to use RDD, and when to use shared file system. Sometimes you work with files, sometimes you work with objects. If you work with text files, log files, PNG files, you probably would store them in a file system. Otherwise, you would store them in otherwise you work with object and you would store them in RDD format. And lastly, I want to move to the pretty cool Zeppelin demo. How many of you actually heard about Apache Zeppelin? So it's a pretty cool UI tool for integrating with various Apache projects and non-Apache projects, and provide some analytics on top of those projects. So what I have here, demo will be very quick. What I have here is Spark, one Spark node, one Ignite node, and I loaded about 6 gigabytes of, what is this? Ah, my demo.
That's okay, I have a better one.
I'll be quick.
Where's the high availability in your
Exactly. Can't list without it. Can't leave without demo. All right, let me try really quickly. I'm going to start node. And I'm going to preload about 6 gigabytes of data into Ignite cluster. Spark cluster, I'm hoping, since I didn't use IntelliJ for Spark, I'm hoping that the data is still there.
So, just to be clear, when you're saying Spark cluster, you don't mean Spark hardware, right? Because for some old-timers like myself, Spark cluster means Spark hardware.
Yeah, it means Spark with a K, not Spark with a C.
Okay. Thanks for this ambiguity.
And what cost? Do you have about the same demo I'm about to run? Is the demo pretty close to this one?
Sort of.
I have some.
There is
skill
zip as
process.
well.
I gotta kill it. All right, I'm gonna give it one more chance. All right, the data is being loaded. 2 minutes, or less. All of that was already prepared before I started. Almost done. All right, so we're done. We loaded some data into Ignite cluster. The data is indexed. I have Zeppelin running. I have Spark running. Spark cluster. Spark node running, not cluster, I would say. And what I'm going to do, so I'm going to run a couple of queries on top of Spark and on top of Ignite, just to see the difference.
Could
So,
you zoom in a bit?
I'm sorry.
Could you zoom in a bit?
Zoom in. Okay. About now? Okay. So here's the Spark side of things, and the Ignite is on the other side. I'm going to run this query. Select, I'm doing a double join on the person, making sure that I want to select all people, their managers. Manager is also a person where manager ID is not now, and their organization names. So triple join, running on top of Spark.
So what is the size of those tables that you're joining?
So the total data set is about 60 gigabytes.
60?
It's all running on my local laptop. There's no cloud. There's none of that. So it's all on my local laptop.
On your laptop?
Yes.
Okay.
All running on my MacBook. So this query took in Spark 21 seconds. We got all the persons, their manager names, and their organization names. Simple join. There's also another query that I'm going to execute that selects organization name and average salary for people. For people that are not managers, that are managers. Manager ID is null. So I'm going to run this. And again, it's going to take a little bit of time in Spark. The reason it takes this long to Spark is because Spark doesn't do indexes. Joins will be slow, group bys will be even slower because it has to do full scan. So that's how long it takes in Spark. And then I'm going to run identical queries in Ignite, so you guys can see the difference. All right, and this query took 26 seconds. So now let's switch to Ignite. I have absolutely identical query in Ignite. I give Ignite integrates with Zeppelin, so I give direct Ignite SQL to Zeppelin. I'm going to run pretty much the same identical SQL query. Executed, done. All right, so just to make sure that I didn't hard code values, change some value, executed, done. So this is the order of magnitude that Nikita was saying, how you can get acceleration with in-memory computing when it's properly done.
So do you
Ignite will generally be 1,000 times faster whenever the query is indexed.
In some sense, I think we're comparing apples to oranges. Do you have a performance comparison with MemSQL? How does Ignite compare with MemSQL?
We actually have performance comparison pretty much to all the other in-memory technologies. I'm not sure where I would compare Ignite to MemSQL. We have plenty of benchmarks against Oracle, and we do very well in those.
Do you have a comparison with VectorWise?
VectorWise, I don't even know what that is. VectorWise, what? It's a database?
VectorWise is the fastest columnar database. It's been around since 2005. Was developed at CWI as X100 on top of MongoDB. Was acquired by Ingress in 2009, and it's productized as VectorWise, or I believe they changed the name to Vector.
Right, I
Okay,
haven't heard about that database.
All right, so that is the industrial reference for in-memory database performance.
Well, I mean, the benchmarks are available. Apache Ignite is an open source project, and we welcome all sorts of contributions if you guys want to contribute your own benchmarks.
Have you run TPCH?
The transactional benchmarks, there's...
TPCH is not it's not an OLTP benchmark. It's a decision support analytics benchmark.
No, we have not run TCP.
Okay.
But we've run this, and here's the result. Spark 22 seconds, Ignite 22 milliseconds.
Okay,
Uh,
fair enough.
all right, any questions about what you just saw?
Can you run the second query? There was two queries, yeah?
Yes, so I can run the second one. Done. All right, so again, we get average salary, organization name, and some other stuff. So Zeppelin is actually a pretty cool tool. You get some pretty cool graphs with Zeppelin, so do check it out as well. So again, we're not doing anything magical here. We're just doing indexing, and Spark doesn't. So the
When
question
you're saying
is,
indexing, what kinds of indexes do you support? Are they bit trees, cache indices, bit vector indices? You know, there
I
are.
have to wrap up, so I'm going to have to take
Okay.
the questions afterwards. I'm actually being told to that I'm way out of time at this point. All right, so any more questions? Please find me after the presentation. I'll be around. So that's it for me. Thank you.